Yes, welcome everyone to GeoHug. So before we kick off today's session, I'd just like to take this time to acknowledge the traditional lands which we're all coming from today. I'm here on the beautiful lands of the Gadigal of the people of the Aurora Nation, and I'd like to pay my respects to the elders past, present and future. So I'm thrilled to have Ray Cas with us today. So Ray is the Emeritus Professor in the School of Earth, Atmosphere and Environment at Monash University and a visiting professional research adjunct at Codes at the University of Tasmania. So he's internationally best known in the field of physical volcanology, including eruption and dispersal processes in subaerial and submarine settings, the hazards posed by volcanic eruptions, and the natural resources that are produced by volcanoes. So it is going to be wonderful hearing from him today about geodynamic influences in the volcanological, what a tongue twister, volcanological, paleoenvironmental and tectonic evolution of the Archean Kalgoorlie Terrane in Western Australia and the implications for the Yilgarn Craton. So it is going to be an awesome session. I hope you all enjoy it. Please use the chat and you'll have the chance to jump off mute and we'll open up the floor at the end. And yes, thanks so much, Ray, for joining. It's amazing having you.
Okay, thank you very much, Jess, for the invitation to give this talk. This talk, or a version of it, was actually given at the 2021 Geological Convention in Hobart. The schedule of the talk was a little bit unfortunate. It was at about 5 o'clock on the last day of the conference. So I suspect that many people are already here heading to beer o'clock. So some of you may not have heard this. But I have just updated it a little bit, and it represents a summary of research that I've been involved with a number of colleagues who are listed as co-authors on the title slide here, and also supported by the Australian Research Council, Goldfields, Independence Group, Silver Lake Resources, and the Geological Survey of Western Australia. So I'd like to thank all of those organisations. I've already seen a few people that I know, so hello to those of you who I know. And then secondly, hello to those of you who I don't know. So I think I've covered all bases there. So I'll get on with the talk now. So the research we undertook was basically to develop a better understanding of the stratigraphy, the lithophases, the eruption processes, the paleoenvironments, and the chronology of events associated particularly with the Kalgoorlie Terrane, but also the neighbouring terrain, the Konalpi Terrane, and then we'll consider what the implications might be for the broader Yilgarn Craton. So to begin with, plate tectonics basically is a pretty good tectonic paradigm, particularly for the Phanerozoic, and it's also widely accepted as being valid back into the Proterozoic. But there are some questions about the degree to which it also applied in the Archean. Now, we all are familiar with the essentials of plate tectonics. So basically, new oceanic crust and lithosphere is generated at mid-oceanic spreading ridges, shown in the circled green area there. And then the lithospheric plates are recycled back into the mantle at deep ocean trenches, which occur either at the margins of continents such as South America or underneath and associated with island arcs such as those in the Western Pacific. Now, one of the essential pieces of physical geological evidence for seafloor spreading lies in the stratigraphy of oceanic crust. And you'll remember that layer one of oceanic crust consists of fine-grained sediments, hemipelagic and pelagic sediments, not shown in this particular cartoon, which overlie the volcanic layer that makes up much of the ocean floor, which is known as layer two. It's basaltic in composition. It consists of massive to pillared lavas. And those lavas are fed by an underlying sheeted dike complex. So this is a system of vertical dikes which are just stacked side by side. And basically, as the lithosphere drifts and migrates away from the crust of the mid-oceanic ridges, a new dike is injected to feed magma to the seafloor where that's erupted as seafloor lavas. And then the next split and the next dike is intruded. So the physical geological evidence of seafloor spreading and the lateral movement of the plates is critically in this sheeted dike complex. And then beneath the sheeted dike complex, we have the sort of cumulate and intrusive plutonic system, which is basically known as layer 3. So, and that diagram, by the way, this is a bit of self-promotion, comes from a new book that's going to be released at the beginning of next year. And I'd have to thank Nathan for helping to prepare aspects of that, that book when he was still at Monash. So when we get to the Archean, there are some problems with basically finding adequate geological evidence for plate tectonics. So there's a lack of convincing slices of ancient oceanic crust, or ophiolites as they're known in old orogenic belts. These represent overthrust or abducted slices of oceanic crust. And within those oceanic crustal slices, we should see that preserved stratigraphy of oceanic crust that I just outlined. There's also an absence of high pressure blue schist metamorphic belts, which represent the high pressure zone of subduction, where off-scraped sediments and slices of downgoing basalt are basically metamorphosed to high pressure metamorphic assemblages called blue schists. And then also to really validate subduction related to plate tectonics and seafloor spreading, we need to find evidence of accretionary prisms, which basically represent en echelon stacks of fault slices of off-scraped sequences of sediments and sometimes bits and pieces of the basaltic layer 2. So these three pieces of geological evidence that would be evidence of plate tectonics and seafloor spreading are very difficult, if not impossible, to find in the Archean rock record. So that then, of course, poses the question as to what were the drivers for Archean magmatism and what were the geodynamic paradigms that existed during the Hadean, if you like, the first 500 million years of Earth history, and then into the Archean from 4 to 2.5 billion years ago. Now, this is a really important part of Earth history. It represents almost 45% of Earth history. So those of you that haven't worked in the Archean, you've only worked in about 50% of geological and Earth history time. So we do, as geologists, need to get a good understanding of the Archean. So in terms of setting the geological scene, we're going to focus on a tectonostratigraphic terrain known as the Kalgoorlie Terrane, which occurs here in the central part of the Yilgarn Craton, which is a typical granite greenstone Archean craton located in southwest and Western Australia. And the Kalgoorlie Terrane has a recorded geological history extending from about 2720 to 2650 million years ago. So that's the Kalgoorlie Terrane there. Adjacent to that is the Komatiite Terrane. And on the right there is a diagram from a paper by Sarah Jones et al., published in the Australian Journal of Earth Sciences in 2020, which shows the general geology of the Kalgoorlie Terrane, shown here, highlighted here, and the Komatiite Terrane, highlighted there. Now, I'll just briefly explain those colours. The purple and the greens represent the basal stratigraphic sequence dominated by basalts and Komatiites. The fawn-coloured belt represents the middle stratigraphic sequence known as the Kalgoorlie sequence, which is dominated by felsic volcanics and associated sediments. And then the brown belts represent the younger stratigraphic sequence known as the late basin sequences. Now that geology is represented here again, and from using another figure from Jones et al. And it shows this threefold large-scale stratigraphic subdivision into the basaltic and ultramafic lower sequence extending from 2720 to about 2690, the Kambalda sequence, the middle more felsic sequence known as the Kalgoorlie sequence, extending from 2690 to about 2665 million years, and then the youngest late basin sequences extending from 2665 to about 2655, although it could be a little bit younger. Now, also shown on this really helpful figure is the timing of granitoid plutonism in the Kalgoorlie Canalpi region at the time. And you can see that the high calcium and mafic granitoids, which together constitutes what is known as the TTG suite, that's tonalite, trondhjemite, and granodiorite, were essentially emplaced during the time when this stratigraphic sequence was actually being deposited on the seafloor. So we have contemporaneous plutonism and formation of supercrustal stratigraphy. And then the low calcium granites and also the more potassic cyanitic plutons, which represent a 5%, perhaps 10% of the plutonic system, they were basically emplaced during the last phases of supercrustal stratigraphy formation, and then post-dating that and coinciding with the principal phases of compressional regional deformation. That is the D2 to D4 deformational phases. Now, these are the sort of traditional phases of deformation. I know Richard Blewett, who I also saw earlier, has proposed a more detailed subdivision of those phases and stages of deformation using alpha subdivisions. And what you'll also notice here is that prior to the onset of these compressional and transpressional deformational events, there was a period of extension, or if you like, atectonic tectonism, when the best we can say is that there was no compressional deformation, but it does coincide, as I said before, with the emplacement of the TTG suites of granitoids. Now, to get a better understanding of the geology of the Kalgoorlie Terrane, what I'd like to do is go through the principal lithofacies that are represented in each of these major sequences. And so we'll begin with the basal Kambalda sequence ranging from 2720 to 2690. We can call this, if you like, stage one in the evolution of the Kalgoorlie Terrane. And we'll begin in each of these stages with summarizing the characteristics of the sediments, the ambient sediments. Now, these are crucial to helping us understand what the paleoenvironment was at the time that not only sedimentation occurred, obviously, but also the environment into which volcanism occurred. And what we find during stage one is that from the southernmost end of the Kalgoorlie Terrane, for example, around Kambalda, to the northern end of the terrane up near Jundi mine, the principal background sedimentary facies are these black to grey laminated mudstones and occasionally some silicious cherty horizons, from which, in some cases, some zircons have been extracted, suggesting that some of those could be felsic tufaceous in origin. There are no coarse clastics, and there are very few intervals of coarse sandstones. So what this tells us about this suite of mudstones are all variably metamorphosed from sub-green schist up into upper green schist and lowest amphibolite, but we can always recognize this mudstone character. And what that tells us is that the paleoenvironment throughout the Kalgoorlie Terrane was an open ocean. The black mudstones indicate anoxia, so lack of oxygen, which of course at that time was not unusual because there wasn't a lot of oxygen in the atmosphere anyway, but just generally a deep and quiet water setting away from any landmass. Land masses, nearby land masses, would shed coarser clastics into the basins. And we'll come back to the significance of that with the younger stages. Then also in this sequence, the Kambalda sequence, we have widespread basalts, and they range from being tholeiitic beneath the Komatiites with which they're intercalated to high magnesium basalts above the Komatiites. And these extend for 500 to 600 kilometres along strike from Kambalda in the south, again right up to Jundee and further north in the north. There are cogenetic dolerite sills in various locations along the belt, and the principal basaltic lithofacies are pillow lavas, massive lavas, and associated hyaloclastite breccias. Hyaloclastite breccias result from cooling, quenching, in situ granulation of hot magma when it comes in contact with really cold water. It just immediately chills to solid glassy rocks and then just shatters in situ, forming these blocky breccias, which often have in situ jigsaw fit textures. These are not explosive in origin. In fact, we have absolutely no evidence of basaltic pyroclastic deposits associated with any of the basalts, or for that matter, the Komatiites. Now that's again important because it again tells us that the environment was a very deep submarine environment, and basically, very importantly, water depth and hydrostatic pressure due to deep water would have been effective in suppressing any explosive steam interaction between the erupting hot basalt magma at 1200 degrees centigrade and, of course, the cold seawater. In shallow water under lower hydrostatic pressure, you could expect to get a lot of steam and what we call phreatomagmatic explosive activity, of which we should find deposits. We don't see those. So the coherent facies and the autoclastic facies are again consistent with a deep water setting. And the third principal lithofacies type in the Kambalda sequence are the Komatiite lavas and the associated sub-volcanic intrusions. Now, these are mostly plus or minus 10 years, about 2.7 billion years in age. Again, they extend along the entire strike length of the Kambalda, the Kalgoorlie Terrane. And the lavas are dominated by the typical spinifex to orthocumulate zoned submarine lava profiles. We see that profile here from drill core at the McCloy prospect or deposit at Kambalda, with random spinifex, parallel or blade spinifex, passing into this nodular orthocumulate. It's like a porphyritic komatiite with phenocrysts of olivine suspended in finer ground mass. And also associated locally, we find jigsaw fit blocky hyaloclastite breccias of Komatiites. Now, we think that based on the distribution of both the Komatiite lavas and also sub-volcanic sills, which I'll just mention in a minute, that basically there were multiple eruption points along the extent of the Kalgoorlie Terrane from south to north. Now, the sub-volcanic Komatiitic or dunitic sills that are associated with some of the lava sequences are very diagnostic. They are dominated by cumulate textures, the coarsest of these really coarse, fully crystallized adcumulate textures. These are centimetre to 3 centimetre diameter crystals or pseudomorph crystals of olivine that have now been serpentinized in this particular bit of drill core from Mount Keith. And the margins of these subvolcanic intrusions sometimes develop orthocumulate. Rarely, and very rarely, will you see spinifex at the margins of Komatiite intrusions, usually only if those intrusions are very, very thin. Now, although the bulk of the volcanics in the Kalgoorlie Terrane are mafic and ultramafic, north of Kalgoorlie, there are some interleaved dacitic lavas and intrusions interleaved with the Komatiites in particular, but sometimes also the basalts. And these are the first, but there are minority component of felsic magmatism associated with the Kalgoorlie Terrane. Here's a nice cartoon diagram that Fiorentini et al. Put together to show the comagmatic and contemporaneous emplacement of seafloor spreading massive and low-bait komatiitic lavas, also feeding sub-volcanic sill-like intrusions, which contain these central or core zones of coarse adcumulate. Understanding these different facies is important because they do contain different styles of nickel sulfide mineralization. So the Komatiites are the principal source of nickel sulfide on Earth today, largely from the Archean, in both the seafloor lavas and the sills. You can get zones of massive nickel sulfide, particularly at the bases. Particularly in the sills, you'll get quite a lot of disseminated ore, and that's quite important, for example, at places like Mount Keith. And disseminated ore is less important with the lavas. So the volcanological setting, basically, of the Kambalda sequence between 2720 and 2690 was basically of a large submarine igneous province. So in the modern plate tectonic world, particularly with plume-fed settings, there are mafic large igneous provinces. But here, as proposed by Barnes et al. In 2012 and Heyman et al. In 2015, we think we've got a submarine Archean example. And basically, we think these were basically generated by mantle plumes. And this is consistent with the high melting temperature, the liquidus temperature of Komatiite magmas, at least 1600 degrees centigrade, and also the abundance of nickel sulfide deposits in the Kalgoorlie Terrane, which is indicative and suggestive of deep mantle sources. And this cartoon here shows a rising mantle plume and then a plume head diverting into the proximity of the Kalgoorlie and Kernalpi terranes in a figure from Barnes et al. 2012. So to visualize this, let's take a modern flood basalt province like the Columbia River flood basalts in the Western United States. These are about 14, 15, 20 million years old. You can see that they're made up of just these stacked sheets of basaltic lavas, in this case, no Komatiites, but let's put them underwater, take the trees away, and that's basically what the seafloor would have looked like during the Archean in the Kalgoorlie Terrane. So now we go to the second stage of development and evolution of the Kalgoorlie Terrane, represented by the Kalgoorlie sequence, which is also widely known as the Black Flag group stage of development of the Kalgoorlie Terrane. And there are some significant changes to the geology and the stratigraphy in the Kalgoorlie Terrane, coinciding from about 2690 and younger. So first of all, there's a major increase in felsic volcanic products. These are mostly dacites, there are minor andesites, there are very minor rhyolites, and many of the dacites have TTG affinity, which suggests a comagmatic relationship with the plutons, which were beginning to be emplaced, of course, during this particular period of time. There's also quite a lot of felsic volcaniclastic sedimentation. And this, as I mentioned, is the time when TTG granitoid plutonism really kicks in. No Komatiites, there are still basalts intercalated in the general stratigraphy, and also some associated comagmatic dolerites, which are really important in terms of ore deposit prospectivity, including, of course, the Golden Mile dolerite in Kalgoorlie and the Cave Rocks dolerite down at Kambalda. Okay, and these are important because they tell us that there was still an ongoing mantle influence that was perhaps the heat engine for most of this felsic magmatism that basically appears at this particular time. So let's again look at the principal lithofacies. And again, black to grey, dark grey mudstones are widespread throughout the terrain, again representing hemipelagic, just suspension settling of background sediments, and again indicating an ongoing ambient deep water environment where this fine sediment just basically settled to the seafloor. A very important new sedimentary lithofacies are volcanic conglomerates and associated sandstone turbidites. Now, what's really important about these conglomerates is the composition of the class, or if you like, their provenance. So an important observation straight away is that they lack metamorphic basement-derived debris. And that would suggest to us that they're not the result of the typical sort of coarse conglomerate alluvial fan systems, which are associated with modern and plate tectonic collisional orogenic belts. These collisional orogenic belts cause the uplift of huge mountain systems, for example, the Himalayan mountains, where India collided with Asia, and then uplift of older basement, and then the erosion and the shedding of that basement debris into the surrounding alluvial sedimentary plain and fan systems. So it would suggest that we're not dealing with this type of orogenic basement uplift derived tectonism to generate these conglomerates. When we do look at the compositions of the clast, we can recognize a class that are derived from the local volcanic stratigraphy. And they do come in various associations, these clasts. Some of the clasts in the conglomerates are totally felsic. Some of them are mafic, felsic, and granitoid. Some of them are just mafic. Some are mafic and komatiitic assemblages. And the mafic and the ultramafic class can be tied compositionally directly to the underlying Kambalda sequence of stratigraphy that we've just reviewed. Now, the granitoid class appear to be intrabasinal TTG sourced class. So this indicates that at the time that these sediments were actually being generated, eroded, transported, and then deposited, TTG granitoids were actually becoming emergent and available for erosion. Now, to cause erosion, and particularly to generate rounded clasts, it requires these source rocks to be uplifted above sea level into subaerial environments where they're subjected to subaerial fluvial erosion and reworking, as well as shoreline reworking, erosion, and then resedimentation. And given the bulk of the provenance being volcanic, plus some granitoid class, it indicates that within the Kalgoorlie Terrane sedimentary basin, if we can call it that, there were nearby emergent islands, some of which at least were volcanic, and some of them were probably granitoid, and there were erosional environments and shorelines which were generating these sediments. So this is really important to understand the significance of the provenance, the composition of the class in these conglomerates. So here's from a paper by Heyman et al. From a study that we did at Agnew, showing some of these different assemblages of conglomerate class. So on the two left-hand pieces of drill core, felsic and granitoid and mafic. So felsic, mafic, granitoid. The central two are mafic and komatiitic. The right-hand ones are felsic and mafic. Now, when we looked at the stratigraphy and the sequence within which the different conglomerates at Agnew or in the Agnew stratigraphy appeared, what we found is that there seemed to be a correlation with the supercrustal stratigraphy, that these then become part of and overlie. So the first conglomeratic sequences seem to have been sourced in large part from basalts and some Komatiites of the Kambalda Sequence Geology. And that trend continues, but in addition, we then start to see the influx of localized granitoids and also felsic volcanic class in those conglomerates, and that then continues higher up in the stratigraphy. So basically, it seems as though the stratigraphy is being progressively unroofed as it's actually forming. So the model that was proposed to account for this conglomeratic class provenance was that we had the Kambalda sequence stratigraphy. It then began to be intruded by TTG plutons, which also generated a volcanic pile, which began to be eroded and shedding debris. And then the pluton continued to rise, volcanism stopped, and eventually the top of the pluton became exposed, and it too began to shed debris into the adjacent basinal settings. In addition, in this Kalgoorlie sequence, there are monomictic felsic tufaceous sandstones, some of which are tens of meters in thickness, but show the bedding profile of turbidity currents. So these are what we call megaturbidites, which are monomictic in the sense that they're showing derivation from a contemporaneous felsic volcanic tufaceous source. Now, these also occur along the entire length of the belt. And to get such large volume explosive volcanism, it means that the vents had to be either very shallow marine or even subaerial. And also it means that large volumes of pyroclastic debris had to be fed into the ocean basin, where these hot pyroclastic flows then ingested water and then transformed into large megaturbidity currents that then deposited these thick, massive, variably graded beds of tufaceous volcanic sandstone at various locations along the terrain. So basically, this requires either or both volcanic rich felsic magmas, shallowing of the volcanic centers, either through constructional growth up to sea level, and or uplift of these systems so that the vent systems did indeed become shallower. So the volcanological setting at the time of a black flag beds or group, or the Kalgoorlie sequence time, was basically of, again, a broad open ocean basin with isolated volcanic islands. Here's an example showing an andesitic or basaltic andesitic stratovolcano in the Aleutian volcanic arc, Augustine volcano, or alternative, if you like, a submarine felsic lava dome, a dacitic lava dome, such as Montserrat in the Caribbean, the magma source of which would have been an intruding TTG granitoid. So we had contemporaneous felsic volcanism and TTG plutonism at this time. Then we go to stage 3, which is the late basins time, extending from 2665 to about 2655 or 2658 as shown here. Again, this is heralded by a significant change in the lithophases. So the late basin sequences, as these are called, are dominated by coarse clastic sediments and also abundant large-scale trough cross-bedded sedimentary structures, such as there and there, and also, again, conglomerates, many of which are channelized and associated sandstones. Now, the abundance of cross-bedded sandstones and, again, rounded class conglomerates is indicative of a widespread tractional fluvial alluvial environment by this stage. And of course, that requires significant regional uplift from the pre-existing marine setting that we've discussed. Now, the late basin sequences can be subdivided into two subtypes. the early late basin sequences, which is depicted largely by the Marugal beds around Kambalda. And these are very markedly tufaceous in their character. Beautiful bipyramidal volcanic quartz phenocryst fragments, and also lots of angular fractured plagioclase phenocryst fragments. So the Marugal sequence was fed by, again, a very significant region extensive dacitic explosive eruption event. It represents the earliest stage of late basin sequences, but the depositional environment was braided river to alluvial fan. And then the late basin sequence, which is typical of much of the late basin sequences in the Kalgoorlie Terrane and the Komatite terranes, are very different in that they're very polymectic. So that means that you've got all kinds of class types, including granitoids, including in places metasedimentary, including BIF class in places, including felsic and mafic and ultramafic class. So it's a real dog's body, but it's indicating that the source for this sediment, for these sedimentary packages, is much farther afield. It's not just the local conglomerates and sandstones that we could relate to intrabasinal volcanoes in the case of the Kalgoorlie sequence. Here we're dealing with far spread regional sourcing of sedimentary provenance. So by this stage, basically the paleoenvironment of the Kalgoorlie, Komatite, and probably many of the other terrains of the Eastern Goldfields province and the Eastern Yilgarn was basically a subaerial, high energy tractional environment dominated by alluvial fans, braid plains, and in places where there were perhaps standing bodies of water, subaqueous fan deltas. So basically the Kalgoorlie Terrane must have emerged from a submarine setting to a largely subaerial one. And basically the question then becomes, what caused this uplift? So let's begin at the beginning. When our solar system first formed about 4.5 billion years ago, all the planets accreted gravitationally, and that accretion of planetesimals and big blocks of rock and debris, etc., created a lot of frictional heat and energy, which caused all those accreting rock masses to basically melt. And that was particularly the case for the inner planets, the rocky planets of our solar system. So when the Earth first formed, actually 4.5 billion years ago, it was actually a molten ball of rock or magma. And then in the first 100 million years of that Earth history, a sort of slowly bits and pieces of crustal platelets, if you like, began to form. And eventually by about 100 million years after formation, there was probably a nearly continuous crustal shell of crust around the mantle and the core of the Earth. Now we know there must have been a solid crust by that time because the oldest dated minerals on Earth are zircon crystals retrieved from the Jack Hills plastic sequence in Western Australia, which generated an age of 4.4 billion years. And that tells us that there must have been some felsic magmatism and certainly a solid crustal shell by that stage. Now, there is no preserved record of this original crustal shell preserved in the Kalgoorlie Terrane, and as far as I know, in the Yilgarn Craton. Although there is certainly some hafnium isotope geochemistry that suggests that there were very old source rocks sourcing some of the younger igneous rocks in the Yilgarn Craton. So we can put across against this hypothesis in terms of explaining the preserved geology. So we certainly see no evidence of the original magma ocean and the original crustal shell. Now that then gets us to that next stage of evolution, which involved the formation of a continuous crustal shell, which is also called a stagnant lid. So basically from the early to at least the middle Archean, it seemed as though there was just a single continuous crustal shell around the whole Earth, as depicted here in this diagram from Bedar et al. And within this continuous crustal shell, which consisted of what we'll call Archean oceanic crust. Now, do not confuse that with Phanerozoic and Proterozoic oceanic crust, because we see no evidence for seafloor spreading in that oceanic crust. It's called oceanic because it was underwater and it was basaltic in composition. So that's why it's called oceanic crust. But basically, there are other planets, for example, Venus, which basically also preserves intact its original continuous crustal shell, or as it's called, a stagnant lid. Now, it's called a stagnant lid because there's no evidence on Venus that that shell, that stagnant crust, was ever broken and then began to evolve into dynamic plate tectonics and seafloor spreading, etc. So what's preserved on Venus are actually the remnants of that very old early crust representing that stagnant lid. And given that there is a lack of evidence for plate tectonics in the Archean, in the Yilgarn, and in most Archean cratons around the world, it's likely, therefore, it's probable that during the Archean in the Yilgarn Craton, there was also a continuous crustal shell or stagnant lid, which was basically mafic to komatiitic in composition, largely because of the mantle source materials which were available to generate volcanism during this time. There was no real emergent continental landmass at the time. Calculations have been undertaken, which I won't have time to go into, which suggest perhaps that there was only 3% of the Earth's surface consisting of subaerial land masses up until almost the end of the Archean. But that doesn't mean that Archean cratons weren't forming. They were forming in the version of oceanic plateaus. So basically volcanism, which was erupting abundant, huge voluminous masses of mafic magmas, both tholeiitic and high magnesium, as we've already discussed, their sub-volcanic counterparts, Komatiites, etc., and beginning to build up a crust or a lithosphere that was at least 30 kilometers in thickness. But because that crust was not particularly evolved, there was very little in the way of felsic material there, it wasn't very buoyant, isostatically buoyant, so there wasn't much in the way of land masses. And the other reason why there wasn't much land mass, there weren't collisions happening. So then we go on to another geodynamic model or paradigm, and these are mantle plumes and probably contemporaneous crustal drips. Now, I've already mentioned that the association of the Komatiites and the basalts in the Kambalda sequence are highly indicative of high temperature mantle plume activity. So I think most people would acknowledge that that is the most likely source of those old and very mafic to ultramafic stratigraphic sequence. So heat anomalies in the mantle, perhaps just resulting from mantle convective overturn and then mobilizing a large volume of deep-seated mantle magma, carrying, in a lot of cases, some of the nickel from deeper sources in the mantle towards the Earth's surface and leading to eruptions of basalts and associated Komatiites. Now, in a lot of tectonic models, there are also, as this Archean crust and lithosphere is beginning to evolve, detachments, delamination processes happening, where segments of the lower crust, which are dense, are being underplated, but basically begin to detach from the base of that crust, begin to sink into the upper mantle, the upper lithospheric mantle, and then begin to trigger partial melting of those delaminated drips that then begin to generate partial melts, which are more felsic and in composition, leading to the onset of TTG type plutonism in the following stages. Now, that early phase of felsic magmatism that I mentioned, that it was contemporaneous with Komatiites and basalts, probably represents some of this initial dripping and partial melting, which then really kicked off in the Kalgoorlie sequence time, where the heat flux from the rising plumes underneath the Eastern Yilgarn Craton then basically generated a lot of TTG melting, including deeper, high pressure TTGs to middle and low pressure TTGs, producing this suite of TTG granitoids that are recorded and preserved in the rock record. Now, this idea of plumes has a long history in terms of understanding and explaining Archean tectonics and magmatism, including some of our own scientists. Ian Campbell, for example, at ANU, was a very strong advocate of plume magmatism and geodynamics decades ago. And then the advent of the drip component to the generation of TTGs is somewhat more recent, but it's certainly been widely accepted. Now, as these granitoids start to rise through the crust, they actually rose to very high levels in the stratigraphy, such high levels that they've intruded the supercrustal sequences that we've just reviewed. So in other words, a lot of these granitoids are virtually contemporaneous in age with the supercrustal sequences that they are intruding, which is really important in terms of, for example, the model that we proposed for the uplift, the unroofing of these TTG plutons, then beginning to shed a granitoid clasts into the surrounding basins. Now, that sort of tectonic paradigm is known as granitoid diaparism. So in other words, the plutons have a lower density than the rock sequences that they're intruding up through. So therefore they're buoyant and therefore they continue to rise. But adjacent to those updoming supercrustal stratigraphic sequences that we can see represented there in that figure, we start to see the down warping or the downfolding of those supercrustal sequences in a process that's, again, for quite some time been described as sagduction. And what that then produces in terms of a final structural stratigraphic architecture is dome and keeled associations. Now, this is also depicted here in this lower map, which again comes from Sarah Jones's paper in 2020, which shows these TTG granitoids in the Kalgoorlie and the Kurnalpi terranes. And what you'll notice is that the stratigraphy around these plutons have been wrapped around. So in other words, you get a concentric warping of stratigraphy around these updoming and intruding plutons. In addition, there are foliations, concentric foliations. These dotted traces here represent pluton margin concentric foliations, which dip away from the margins of the plutons. And in addition, there are lineations shown here by these arrows, which radiate orthogonally away from the margins of these plutons. So basically what we're seeing in terms of tectonics here is dome up, greenstones down tectonism, which is actually preserved in structural fabrics around these plutons. So this is not geofantasy. There is actually very good geological evidence. So then in the late Archean, we know, of course, that the Yilgarn Craton is actually penetratively deformed. The seismic surveys, which were commenced in the 1990s and early 2000s, have provided a beautiful structural profile through the Yilgarn Craton, which shows the stacked and imbricated stratigraphic sequence and also large antiformal and synformal structures. So here we are seeing the effects of regional scale tectonic convergence and on echelon stacking. So this means that there is a fundamental change in the geodynamic tectonic regime at this time. And we think this is recorded in the stratigraphic record via those late basin stratigraphic sequences, which are highly polymictic in their character. They represent the onset of convergent collisional tectonics, compressional tectonics, uplift of not only the supracrustal sequences of the Yilgarn, but perhaps older, deeper seated crustal basement sources, shedding of that debris, and then, of course, leading to the overprint of the D2 to D4 compressional deformational fabrics, which have long been recognized in the Yilgarn Craton, and particularly in the Eastern Yilgarn Craton. And very importantly, the timing of those D2 to D4 convergent compressional deformations coincides with the onset of late basin sedimentation and then continues beyond that. And we would suggest that this represents what is known in the literature as mobile lid to subcretion type tectonics. It's represented here in this diagram, again from a paper by Jean Bédard, who's done a lot of work in the Archean in Canada, showing basically, if you like, the onsets of initial stages of craton margin subcretion or subduction, not necessarily to high depths, until we start to see the development of metamorphic assemblages, including eclogites, which do indicate high pressure deformational and metamorphic assemblages. So this localized subcretion focused on the more rigid craton margins then represents a transition into plate tectonics from the end or the very late Archean and then into the Proterozoic. Now, in addition to that, here is a little bit of geofantasy. We know from the history of the solar system and from the history of the planets that at least from the origin of the Earth to about 3.9 billion years, that all the planets, and particularly the inner planets of the solar system, were subjected to heavy bombardment by asteroids and bolides. Now, further work has been done on this and has indicated that asteroid and bolide bombardment probably continued in a waning manner to the end of the Archean. And this has been documented by Botke et al. And also modeled. And they basically suggested that there were 15 bolide impacts involving asteroids in diameter between 20 to 30 kilometers and at least 70 10-kilometer diameter bodies. Now, large bolide impacts basically on a relatively thin lithosphere would have the following effects. Those bolides would penetrate through into the sublithospheric mantle, cause high temperature melting of a large fraction of the mantle, perhaps as much as 40 to 60%, resulting in large igneous province volcanism and plutonism, Komatiites, high magnesium, non-arc basalts, ultimately evolving into TTG granites and associated volcanism. And there is actually geological evidence for these impact events via spherical layers. These are basically spheroids of what appear to be melt droplets and high temperature and metasomatized fragments of debris that are dispersed in continuous layers within some of those marine sequences that are typical, for example, of stage 1 and stage 2 of the Yilgarn Craton. But these have been documented in many cratons around the world during the Archean, and including particularly in the Pilbara Craton to the north of the Yilgarn. So basically, heavy bombardment is likely to have occurred and could explain, for example, the onset of, for example, Komatiitic and associated mafic magmatism, and then the subsequent evolving morpholsic magmatism. In a paper written by Tim Johnson from Curtin et al. Just a few months ago, they've actually reconstructed the stratigraphy of the Pilbara in terms of such a bolide impact model, ranging from initial impact over about 3.6 billion, and then working through the stratigraphy and the various associated plume, drip, associated derivatives of that impact event, and the associated volcanism and sedimentation, accounting for the stratigraphy, and really not involving no necessary involvement of plate tectonics to account for the stratigraphy or the geochemistry of any of those successions. So in conclusion, getting back close to home where we started, as the stage 1 Kambalda mafic and ultramafic sequence certainly can be documented as a record of mantle plume geodynamic regime. There was certainly no compressional tectonics at that time. There may have been slight extension, although I don't see a great deal of evidence for extension, or it was simply just an atectonic setting, nothing much happening. And of course, there is the possibility that that was all triggered by a bolide impact. So that's a possibility there. When we go to stage 2, morpholsic Kalgoorlie sequence, we think that there's an ongoing impact of plume activity, basically triggering large-scale felsic volcanism and also regionally extensive diapiric plutonism, which is represented in both the volcanics and the CTG plutons. We see no evidence of linear arc-like magmatic belts, and basically the plutonic diapirism then caused progressive regional scale shallowing of the basin at that time, producing in response those volcanic conglomerates, and ultimately that uplift evolving into the uplifted, mostly subaerial stage 3 late basin successions, which then, with the late basin polymictic sequence, heralds the onset of regional compressional deformation, perhaps crustal subcretion, and the transition to plate tectonics, which also coincides with the onset of more potassic plutonism and orogenic gold mineralization in that period from about 2630 million years and onwards. So I'll leave it there, and I'm happy to try fielding some questions.